Road to Olympiad.
Welcome to RTO. Consider the following problem. Determine if there exist 4 quadratic equations such that the sum of any 3 of them has real root, while the sum of any 2 of them does not. We are dealing with problem involving the roots of quadratic equations. It is pretty straightforward that the first thought is to check the discriminant. But to check the discriminant of sum of 2 or 3 quadratics is not an easy job. Here, we are going to talk about another common way of identifying whether an equation or polynomial, not necessarily quadratic, has real root or not. Pause the video if you like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve these problems, we start by letting the quadratic polynomials, which are responsible for the 4 quadratic equations, to be P1, P2, P3, and P4. And let's consider the following arrays. Notice that if we add each columns, we get twice the sum of any 3 polynomials, which have the same root as the sum of the 3 polynomial itself. Since the sum of any 2 of them has no real roots, that means each of the entries in the array must be strictly always positive or always negative, so that the graph does not pass through the x-axis. However, since the sum of any 3 of them has real roots, that means the sum of the columns is not strictly positive or negative. This is to say that the 3 entries in each columns cannot be all having the same sign. Else, this will imply that the sum of the 3 polynomial will either be positive or negative as well, and thus not having real roots. So consider the first columns. Without loss of generality, we can assume that P1 plus P2 is positive, P1 plus P3 is also positive, while P2 plus P3 is negative. Notice that from the second column, P1 plus P2, P1 plus P4, and P2 plus P4 cannot be all positive. And since P1 plus P2 is already known to be positive, this means that at least one of P1 plus P4 or P2 plus P4 must be negative. For the similar argument, we can come out with P1 plus P4 or P3 plus P4 must be negative, as well as P2 plus P4 or P3 plus P4 must be positive. We see that P1 plus P4 cannot be positive. Else, one of the second columns or the third column will have all the entries to be positive, and thus the sum of the column is positive. Therefore, P1 plus P4 must be negative. Now, notice that from P1 plus P3 is positive, we have P3 must be greater than negative P1. Also, from P2 plus P3 must be negative, we have P3 is less than negative P2, which combine together to give us P3 is between negative P1 and negative P2. This implies that P1 itself is greater than P2. And from the fact that P1 plus P4 is less than 0, we know that P2 plus P4 must be less than 0 as well, because P2 is less than P1. By using a similar argument, we can come out with the result that P3 plus P4 must be negative as well. However, this is a contradiction because it will make the sum of the 4th columns to be negative. Therefore, there does not exist 4 quadratic equations such that the sum of any 3 of them has real root, but the sum of any 2 of them does not. And this marks the end of our solutions. Post in the comment below if you have any thoughts on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.